Okay, just want to have a quick run through some of the work that's been going on getting the multi-core communication support going for the i.MX8M Mini EVK. Over here we've got the main serial output from the i.MX8M Mini. If I just power cycle the board there, we boot up, and we're just going to break into U-boot there. Now in the top left, we've got another serial output, which is from the M4 core itself. So when we start running code on that, we'll see some serial output from there. And if I look at my U-boot, I've got some scripting in the environment variables here. And we can see that I've got a firmware M4 variable set to be rpmsg light ping-pong rtos linux remote.bin. Now that's a standard example that shows us how the M4 core and the main core can communicate between each other, which is the kind of thing I think we're looking for. So I thought I would have a go at getting that going. Now in the MCU Espresso SDK, we have the source code to the M4 binary code that we're going to be running, and if we have a little look at that, this is running on top of I don't know which it is, it's either FreeRTOS or Zephyr, and what we particularly care about is that there's a main app task in here. If I can find it, there we go, and that's doing a bunch of setup, and it's sort of saying, you know, hello, we're running, our link is up, and then it's waiting for some messaging from Linux, from the Linux driver on the main core, and it's sending a response back from this core. So this is what's going to be looping around up to 100 times, and hopefully that's what we're going to see working shortly. Now what we can do is we can then build up the source code there to give ourselves an elf file and a binary file. Binary file is what we particularly care about. That's what I've built here, and that's what I've copied across to the file system on the target, and that's what we're going to load into the M4 core. So if we go back over to U-boot here, you see there's a boot command load firmware, which is essentially just loading that file into the right place in RAM for us to be kicking off the M4 core. So if we run that, now by default that would normally kick off the M4 core as well, but I've disabled that for my own debugging, so we'll just do that manually here. There's a boot aux command which kicks it all off. Kaboom, starting the auxiliary core, and as if by magic you see the serial messaging coming out of that M4 core saying that it started running, and it's now just waiting for the Linux driver end to come up. So if we go back and we allow our boot to continue with the standard boot command, that brings up the Linux kernel, and you'll see the link has been made as the rpmsg driver loads in, and we're now connected between those two cores, but nothing much is happening yet because there isn't anything much happening on the Linux side. So the Linux end that does the messaging here is in a kernel module, and the example is called i.MX rpmsg Ping-pong. So what we'll do is we'll load in that module, and this is going to go quite quickly, so let me just sort of pull this down for you to see. What's going to happen is the Linux is going to be sending a bunch of ping messages. They're going to be responded to from the M4 core, and we should get a ping-pong effect. So here we go. I typed in the password. Kaboom, look at that, fantastic. So the M4 core has been getting pings and sending pongs, and the Linux driver has been getting responses back, which is the incrementing values that are coming back, and then that's all to be expected as it cleans up and finalizes. So basically that's where we are. That's showing that we can get the M4 core running, and we can do comms using the rpmsg implementation to get data backwards and forwards. All needs a little bit of automation, but that'll probably come off the back of the work that needs to be done to sort of put this M4 binary together, which I think I need to have a bit of a chat with you about. But yeah, progress made. Thanks.